Precalculus 1. We have derivatives of rate of change. The previous section was not complete. Network exploded, so the last example will be uploaded as notes only. So here we go with the derivatives of rate of change. First of all, we said that the derivative is a function which generates all slopes of tangent lines, all of them. If we have a function, the tangent line can be drawn at any point, and by you providing the value for that point, the slope for this line would be the derivative at that same value. And if you say that this one is x equals to b, then the slope of this line is the derivative computed at b. And then you can go like that and compute as many of these as you need. We observe the derivative to learn how the system changes. Derivative measures the rate of change. So we already said before that the slope of the secant line, which was first y2 minus y1 over x2 minus x1, which we changed into f of x2 minus f of x1, which is the rate of change, we upgraded that into the slope of the tangent line by adding the limit in front, as this x2 went to x1. And the same, x2 minus f of x1, x2 minus x1. So now, what's happening with this section? Well, first I would like to understand the notation together with application, together with derivatives, all of that at once. I have a point A, and then I want to go to point B, which covers certain distance. Let's call it distance x, in certain time, as I start at t equals 0, and I end up at some time, t1. So that t1 can be an hour or 5 minutes, depending on how fast you are. So now I can calculate the speed, right? The speed as distance over time, but then it's a change in distance, so I can say it's xb minus xa divided by t1 minus 0, and you already see here that rate of change. Now this will be your secant line. So from here I can quickly show that, and please look at the screen now. Look at the screen, because I need to write it and say it at the same time. You need to see this. The change in distance in time is the derivative, and we call that velocity, which is a vector. And if you don't worry about the direction in which you are going, we're just calling it speed, which is the magnitude of the velocity. So if I am changing the distance in time, it is going to be called velocity. Now you should be able to understand this quickly, because let's put a dx dt, right? Because we cover x values along x-axis, say. X could be measured in miles, and time could be measured in hours. And you know that miles per hour measures the speed. So I'm hoping that you are connecting all of these concepts together now. Every time you're talking about the velocity, velocity is change in position. You are covering distance in time. And here is the experiment. I'm going to stand right here. And because I have no velocity right now, it's 0 in respect to the floor, I'm not going anywhere, right? As soon as I have some velocity to it, I'm changing the position. You cannot have velocity and stay there, right? So if you have a velocity, you are changing the position. So here's the position A, the door is position B, and I'm not going to get there until I acquire some velocity. So observe that there is no change in distance. There is no change at all because I have no velocity. As soon as the distance starts changing and I'm closer and closer to the door, I actually have some velocity and I can reach point B at that point. Now that also happens in time. So we would say that you are covering some distance in time. So you are changing the distance in respect to time. And that is the derivative. So we are going to distinguish between the instantaneous and average. Average one is the secant line, and the instantaneous one is the derivative. Because you find the derivative at the point, it gives you the slope. It shows you the change at that instant. When the cop measures how fast you're driving, it measures instantaneous velocity. When you glance upon the speedometer, it is instantaneous velocity. Because that changes instantly as you either hit the brake or push the gas pedal. So instantaneous one is the derivative, and the average one is over time. If you say that it took you an hour to get to New York, right, an hour driving to get to New York, well, you take the distance in miles, you divide by 1 hour, and you know how many miles per hour you draw on average. But you know that you were not driving on that average all the time. You had to, maybe, I don't know, hopefully you do, stop at the stop sign, red light, or if you pull over, right? You stop on those occasions, otherwise just go. So there are those variations in how fast you're driving. So the average one smooths it all out and says, yes, you were going 0 for 28 seconds because you were on the red light, but then you were doing, I don't know, 67 for 15 minutes, and then you hit the traffic, you were doing 15, and so on. So instantaneous is the one that looks at the instant, which is the derivative. It looks at the instant and says, you are going 0 right now. You are going 15 right now. You are going 67 right now, right? That is what the speedometer is reading, or the car. But when you reach your destination and you look back in the past and you say, all right, it took me an hour to get here. On average, I was doing 54. That kind of smooths it all out and says, on average, you were doing 54. So that's the difference between the two. We also have to worry about, from physics standpoint, the difference between the displacement and distance. So to explain that, I will have to draw, let's say, a diagram like this. Let's say this is the home, this is RV, and this is the shop, right? Let's say you live, what was it, 10 miles away? Let's say that ShopRite is 1 mile from RV. And then you need to drive back and you take whatever route. Actually, go back on the same route, doesn't matter. There you go. So now, This is the torque distance versus displacement. So when you go from home to RVCC, they are both the same. So if you go home to RVCC, distance equals 10 miles, displacement equals 10 miles. If you go home to RV to ShopRite, distance is 11 miles, and displacement is 11 miles. If you go home to RV to ShopRite, back to home, distance covered is 11 miles. Sorry, not 11 miles. 22 miles. And displacement is? Very good, 0. So what is the displacement? Displacement is how far you are from your original position at any time. How far are you from your initial original position? So this is where you sleep, right? This is where the day begins. So the displacement, so we take that as a reference point, and we say that if you covered the displacement, you went to RVCC, well, you covered distance of 10 miles, and the displacement from your original position is also 10 miles. If you go the trip like this, you're 11 miles away. But if you go this way and come back, your distance covered is 10 plus 1 plus 1 plus 10, that's 22, but the displacement is 0 because you're back to the position where you started from. So that's the difference between the distance and displacement, and you will have more fun with that when you take, if you take physics course. I will just use that here briefly in one of the problems, so I just wanted to explain that so you guys understand. All right, now let's talk about derivatives. Position function. P of t. So I have some position function P of t, and that position function is some kind of curve on the floor that I follow in time. So a lot of people are confused by this. I don't know why. Just take a piece of chalk, go in front of your house on the street, draw a sign line, and just walk on it. And there you go. You have your P of t. See? It's very simple. Draw a quadratic, walk on it. Draw exponential, walk on it. You can draw any function you want on the floor, on the street, with a chalk, because that is your x and y coordinate system. Look at the floor. There's your grid, right? To the floor. Just draw it down there. You can project from these. Well, too bad that these are rectangles, but you have the square ones. These are 2 by 4, so cut them in half. You have a grid. And you can make this into a grid. So technically taking... Does anyone use right paper in mathematics course in this classroom? What the hell? Line? Oh, there it is. Who's my favorite student over here? Jose Torres. I'm serious. Is he the only one who's using the right paper? Oh, yeah. Thank you, Mom. Oh, you got, but you're not writing in it. You have it in the bag. So I guess it doesn't count. These guys are serious. So, literally, here's the square grid. You put it down. You draw on it the function and just walk on it to let the end go on it or whatever. Well, so from now on you put it on top, so I'm not on. Alright. No, I used to get kicked out of classroom. If I bring in the notebook with lines, That's where my education is. So they say, oh, you don't have the right materials for the class, right? You don't have pencil, you don't have pencil sharpener, you don't have eraser, you don't have a square notebook for any of those reasons. They check. Yeah, exactly. They say school is not for you. Go outside, play ball. Done.
I did that in like middle school, and then as soon as I entered high school, the teachers were just like, "Okay, you have a pen and pencil. If not,
You're lucky, right?
If not, I can give you one."
Yeah, you just lose. All right, so we understand now the position function. I hope position function is going to be whatever function you know, and think of it as function on the floor. And now what we're going to do is we are going to take the derivative of it. So the derivative of the position function in terms of time is going to give us our velocity function. So as soon as you see that you are changing the position function in time, you are getting the velocity function. Now, you can also change the velocity function in time, and we get change of velocity. Acceleration. We have positive, negative acceleration. In a car, you have the gas pedal, which is positive acceleration, and you have brakes, which is negative acceleration. Both of those pedals are changing velocity of the car, whether you want to speed up or slow down. Those are actually these concepts. Very simple. The book doesn't talk about it. I'm going to add it in because it is a physical concept that you guys actually experience every time you drive. Does anyone know what is the change of acceleration in time? Jerk. Jerk. Which is the, if you push on the gas harshly, right, you feel it. You feel it. Very rapid changes in acceleration, and also that is exactly what happens. It's, again, a jerk. When you hit the brakes very hard, right, you go forward. So that's that motion. Now, the book doesn't talk about it. I'm just going to toss it in because I want to show how far we can go with multiple derivatives. Because if you start with a position function being your level ground, which is like f of x, right? Then the first derivative, second derivative, third derivative, right? And they're all in there. So jerk would be the third derivative of position function. Do we see that? We keep taking derivatives. So now I'm going to add that in our notation. I'm going to say further that acceleration is the second derivative of position function. Observe what the squares are on d and t, right? So the velocity, the acceleration is the second derivative of position, and the jerk would be the third derivative of the position function, and the second derivative of velocity.
Exponent with the third one.
It's 3, 3, 2, 2. You mean these ones?
Okay, yeah.
You can't zoom like this in your notebook. Which is why you should all get the surfaces. All right, so now I want to do a problem, and that problem is have to get up. This one. Yeah. What was that motion? Projectile motion? Parabola, thank you. So we're going to have parabolic motion anytime you throw something, it is going to go in a parabolic motion. You start by throwing it, which has initial velocity, but then it's immediately going to start slowing down because of the gravity. And eventually it's going to bend and fall back to the ground. So we're going to have some initial velocity, we can call it V0. There's going to be a max height at the vertex. At that position, velocity in y direction is going to be equal to 0. There's a lot of cool stuff happening there. You are going to start on y0 elevation. So the position function for something like this is going to be negative 1/2 gt squared plus v0t plus y0. That is the position function for the parabolic motion. Now this can be very easily obtained using a differential equation and integration, which you are going to learn in the calculus class, and then you get to use these later on. Yes? We'll see. That's the best answer I can give you right now. We'll see. So now I have a position function. I can take the derivative of it. Let's take the derivative, see what happens. And the derivative is clearly taken in terms of time, which is going to give me velocity function. So the derivative of t squared is 2t. So I have negative 1/2 g times 2t plus v0, derivative of t is 1, and then the derivative of a constant y0 is just 0. Now, do you guys see, if you remember your physics or taking it right now from kinematics, v final is equal to v initial minus gt, which is, this is the acceleration. Do we all see that formula? You remember that one hopefully from physics, if you ever took physics. That's where it comes from, right there. Taking the derivative of velocity function, well, let me just simplify velocity function first. So velocity function now, when this cancels, is negative gt plus v0. Why negative? Because the object is going downwards. Gravity pulls down. And now we're going to take a look at the change of velocity in time, which is the derivative here, and you just get negative g. And that is your acceleration function. Yes? Yeah. So now let's talk about the entire thing put together. We see, looking at the picture first, and I did the experiment. Let me do the experiment one more time. Let's go. Don't worry about it. I'm not going to miss. See? Parabola. Doesn't matter how you throw it. If you throw it very hard like this, it's going to go straight for some time and it's going to fall. Again, in a parabolic. When you start falling, it's going to fall. So you can toss it straight. It will go straight and then it's going to fall down. So parabolic motion looks like this. It's a downward opening parabola, and you see it's negative x squared, right? Negative t squared. So gravity pulls down. Initial velocity is important. because I can do this as well, right? It's still parabolic motion, but it went close because I didn't put too much into initial velocity. And also, the height from which you throw is important. Stats basketball players, they will confirm. And two. So all of these things are important in the formula. Now we take the derivative in respect to time. Derivative of t squared is 2t. Half will cancel the 2, so we just have negative gt. And then derivative of this term, that's a constant, we copy it. Derivative of t is 1. So v0 times 1. Derivative of y0, which is just a number. When I toss this marker twice, I toss it from this height, which is 6 feet. Right? So then we just 6 like that. Derivative of 6 is 0. Constant. So we have the velocity function. And once I have the velocity function, I can take derivative of the velocity function and get the acceleration function, which is this. So that's the part. So now I have all of the equations. Once I have all of the equations, I can start calculating stuff. What is the stuff? How long does it take for object to hit the ground? At what point the object is at maximum height? What is the velocity or acceleration, at the various parts, at the various times during the trip? So we can calculate anything technically, as long as we have the equations that are needed to compute those things. Does this make sense? Of course, math and physics. All right. Time flies when you're having fun, right? So should we compute something with this? Yes, no? Or go to do business? All right, let's see an example. A stone thrown vertically on Mars. Suppose a stone is thrown vertically upward from the edge of a cliff on Mars, where the acceleration due to gravity is only about 12 feet per second squared. Mars is smaller than Earth. We have negative, right? We have 32.2. Mars is 12. At the initial velocity of 64 feet per second, from height of 192 above the ground, find the height. So even though they give you all of these things in the text and you should be able to put it together, they call the position S in a textbook, which actually makes sense because there is an S in the word position, right? Position. So S of t, that makes sense. So S of t, better than P. S of t is given as the gravity piece, so minus 6t squared, initial velocity of 64, and then from the 192 height. So we have our position function, emphasis on S. Determine the velocity function, part A. What's the velocity function? The derivative, great. So what is it? Awesome. So we're taking the derivative. T squared is 2t, so negative 12t plus 64 times 1 is 64. Great. When does the stone reach the highest point? Well, what did I say was true? So velocity is 0. Yes. If you are considering only the y motion, and if you're looking at the screen right now, here is the stone. The stone is thrown upward, and then it's going to stop, and then it's going to go back down. One more time. It goes up, stops, and then goes back down. it stops at the max, which means that the y velocity, velocity in y is 0. So, by knowing that, we set our velocity function to 0, and the time we find is the one where we are reaching the maximum. So, velocity equals 0 says that negative 12t plus 64 is equal to 0. So, time is equal to negative 64 divided by negative 12, which is divide top and bottom. Let's cancel. Should just quit, right? So negative and negative cancel, and we have a positive number, and then we divide by 4, let's say, which gives us exactly 16/3, right? Awesome. So now we know it's 16/3 of a second. So that's like 5 1/3 seconds if you want to convert that to know what it is. 5 1/3 of a second. What is the height of the stone at that point? Well, you have the time and you have the position function. Just plug in. So we need to find s of 16/3 minus 6 times 16/3 squared plus 64 what? Times 16/3 and plus 192. So one of the 3's will cancel, give us 2. That's 32. So one of the 3's cancels, so it stays over 3. Sixteen squared is 256 times 2, 512. Plus, now we have to multiply 64 by 16. 16 is 2 to the 4th. So 64, 128, 256, 512. Right? So that's 64. So 120, 128, 256, 512, and then 1024 over 3 plus, and then we also make this one over 3. So multiply everything by 3. That's going to be a 6, and then a 7, and then a 5. Great. So the first and the last work together to make 64. So 1088 over 3. 8 and 8 is 16 plus 1 is... What happened? All right, that's it. Feet. So that's the highest it will reach. When does the stone strike the ground? Well, when does this happen? How would you compute the furthest distance? What?
Isn't that like the time it takes for the stone to reach the maximum height?
It doesn't have to be, because you can throw the stone from here. There was That's exactly what we said. You can throw the stone from here. Can double it. Can we find the zeros of this function here? Right? It's a zero elevation. The height is 0 when it hits the ground. So that's not even a calculus question. You just have to. So for part D, t equals question mark to hit the ground. We have negative 60 squared plus 64t plus 192 equal to 0. And then if you don't want to do this, just put in Mathematica or Wolfram Alpha. It gives you the numbers. And then to find the velocity, you have the time from there. So velocity when a stone hits the ground. And you will just compute the velocity at the time you got from here. And it's going to be some number. So we don't have to FOIL factor now, all these things. So that's the part in physics. If you stop a little bit and think about it, you see the position function as the y motion. In order to get to the maximum point, that's when the velocity is 0 because the object stops, changes from going up to going down. What else? I think that's it. Let's take a look at population. Looks like they will have to leave business for next class because we won't have time for everything. All right. So what do we see from this website, which is tracking the population? Right. So, few concepts that we need to know regarding population is that this planet has a finite surface area, finite resources, finite amount of water, finite amount of resources to make energy because we are still type 0 civilization, which means that we still burn dead plants and animals for energy. And fusion is always 30 years right away. So looking at this, we compute, depending on which model you look at, that the carrying capacity of the planet is anywhere from 10 to 15 billion people. Now, if you go back in the past and you look at 1980s, somewhere in 1980s was half of this population. That's 30 years ago. So we are able to more than double population. So we should be able to reach this critical time times over fairly quickly. The lifetime's here, 30 years or so. So there is a population crisis. You can see how fast the population is rising. You can see the top 10 over there in terms of countries. You would never put the Japan, right, with their 4 tiny islands on this list, but there it is, proud number 10, 126 million, right? No, how it's big somehow. I mean, Indonesia, they have 1,000 islands. That's clear. Brazil, huge, fine, sure. Pakistan, not that big, right? Nigeria as well, Bangladesh, Russia is huge. So, you know, but you can't look at the land. You have to look at the land in terms of how much has to offer. So I want to take the current state. I'm going to call it today's is 2016 as a first point, and then 7.34 billion. And then let's take a look at the population. So and we can see that there was 3 billion in 1960. All right. So now, using these two pieces of information, I am able to come up with the mathematical model using the exponential function, which you should know from your Precalculus 1. Population is the initial population e to the kt. And if you want to set this one to be your initial, you will zero out time. So you would say that 1960 gives us t equals 0. So that point resets to 0, 3. And then the second point immediately resets to what? If 1960 is 0, 2016 is 56, 7.34. So now, since this is our initial point, so this one transformed into that, that one immediately gives us that the P0 is 3. So population in time is 3e to the kt. Now I can use the second point and say that 7.34 billion is equal to 3e to the kt, which is 56k. And we can compute the k, which tells us which is the rate of growth. So we have 7.34 divided by 3 is equal to e to the 56k. And we ln both sides to get closer to k. So 56k is equal to ln of 7.34 over 3, from where we get that k is equal to ln of 7.34 divided by 3, everything divided by 56. And that's going to be a number. If I did this right, on this calculator, we should all have 0.0, and we keep 4 decimals, 1598. So population model would be this one. Now you did this in your Precalculus course, so you should know how to do this when you're giving 2 points, how to find the exponential equation out of those 2 points. If you don't remember it, then section 3.5 in your Precalculus textbook, which you didn't sell after your Precalculus course. Still have it, it's awesome. Now, you can use this model to do many cool things. You can predict the future by it, because you know that if you plug in 56, it's going to give you today's current state. So this starts at t equals 0 is 1960. So if you want to compute the population, let's say you want to compute population in 2025, what would you do?
Instead of 2015,
But what's t for 2025?
if you're considering that you would see as T0,
Yes?
so it would be 65.
65. So you can approximate the population of the world by simply plugging 65 in the equation, push some buttons, and you will get the values.
What about lottery? We calculate the lottery. I'm not sure we're like doing 2,000.
No, it can't be. Otherwise,
We can't do calculus for lottery too.
it's not the same type of mathematics.
I mean, calculate the probability of each individual letter, but or of each individual combination. I feel like they would all be more or less equal. More or less equal.
So, one more thing. What are we interested in here? We are interested to see 2 things. We're interested to see 2 things from this model, and that is what is the limit and what is the derivative. So if I am to take the limit of 3e to the 0.01598t as t goes to infinity, I'm just going to let the time go forever to see how big the population of Earth would be. We would actually get infinity there, which is bad, right? So that shows that this model cannot accurately predict for a long time what's going to happen with population. This model is good on short relations, right? So, 10, 15 years, okay, we can use it, but not for prolonged periods. We can also take the derivative, change in population over time, because at that point we can calculate how many people are added, because you are calculating change per year. So if I take the derivative, it will be 3 times 0.01598 times e to the 0.01598 t. So if I compute that, it will be 3 times this decimal. Well, question without calculator, it's 4, 7 is 9, 15 and 2, and 3 and 1. So this would be your derivative. And now if you plug in numbers into this derivative, you would see how many people are added each year. So let's calculate for this. Yes.
I have approximately 2050 population.
What?
I have 1,000 that 26
I'm not sure where. All the way up?
Little bit up. Yeah. So here you wrote, and from you're taking 1950 as the PBO,
Yes.
and the population is 3 billion.
Yes.
So within a change of 56 years, won't that be the population at 4.24?
What do you mean 4.34?
Because at time T0, there was already population of 3 billion. But after 56 years, there is a population of 7.34 billion.
Yes.
So the difference would be 4.34 billion.
Yes.
So when the population was then 4.34 instead of 7.
No. That is the current population. It's all the people.
But we have to find the rate of the growth, right?
No, we're not finding. That was just to find the model. Now we're looking for rate of growth with the derivative.
Okay.
So we plug here. So I just want to see how much people we add this year. So I'm computing this one at 56, which is 0.04794 e to the 0.01598 times 56. So let's see what we get. Now exponentiate it. And I get that the change of population for our 56, number 56, which represents 2016, is 0.121716, let's say, or 159, whatever. It goes on. So we're going to add about 120 million. 122 million added to the population of the planet just this year. Now you can also see that the population is actually rapidly expanding. Obviously more people, population goes faster because with the 3 billion people in 1960s, time to add 1 billion was 33 years. Today, right, with we can see that it's much faster for us to add another billion. It's not opening. Doesn't matter. When it's 6 billion, you see it 12 years, right? That's almost 3 times faster in 50 years. Or in 40 years, I mean. Okay, so there is one more type of a problem that we'll cover next time, I guess, because I see you guys want to go. It's fine, whatever. I will talk business next time, and we'll continue with other sections. We'll be done with chapters, I would say, chapter 3 in 2 weeks now, right? This Saturday coming up, and then next one, chapter 3 is done, and if you want the test, we can have it at some point. So, happy.